Okay guys, today we're going to be using Trig to find the area of triangles. Also, this is my third time recording this video, so I'm sorry if I'm going a little fast. I'm just a little upset because first time I realized I wasn't recording, and second time my mic somehow was on mute, and so hopefully this will be my third and last time making this video. So if I go a little quick, it's because this is my third time doing it already. So hopefully I'll try to keep at a good pace. But anyway, alright, warm up. We're going to find the area of this triangle GHI. So we can't really use trig on this one because we do not know any of the angles. Right? We don't know the measure of any of those angles. Also, this is not a right triangle. So we're going to do this the good old-fashioned way, the way we would do problems like this before we knew any trig. And let's see if you guys can do this. So try this for a warm-up. This is actually a pretty difficult problem, right? But give it a shot. Alright, hopefully you gave it a shot. But let's see how we're going to do this. Alright, so it's a triangle. We know the area of any triangle is 1/2 base times height. Alright, so let's draw in a height. And I think we would all agree this is the easiest height to draw in. So I'm going to call this length GHI J. So that height HJ, I drew in an altitude, right, is going to be my height. So my area as of right now is 1/2. If I'm using that as my height, my base is 15 and the height is the height. So let's try to figure out what that h is equal to. So once I draw in this height, I notice I have two right triangles. So what I'm going to do is try to label the legs of each of the two right triangles that are created. So if the entire thing is 15, I'm just going to call this x, and if that is x and the entire thing is 15, well, this segment JI would have to be the entire thing, 15 minus x, and so that's 15 minus x. Alright, if you're thinking this is a Hills or a SAS problem right now, it isn't, because that is not a right angle, right? Hills and SAS only works when we draw an altitude from the vertex of a right triangle. So never said GHI was a right triangle, so not a Hills and SAS. So again, we're looking for h. I have two right triangles. Let's apply Pythagorean theorem 2 times. So doing it on the left triangle GHJ, we can say x squared plus h squared equals 7 squared, or 49. Applying it on the right triangle, on triangle HJI, we're going to have leg, let's do this leg first, 15 minus x, in parentheses squared, plus the other leg, which is h squared, equals 12 squared, which is 144. Alright, we were trying to solve for the height, so I'm going to solve both of these equations for h squared. So here, h squared equals 49 minus x squared. And in the other triangle, h squared is going to equal 144 minus, I'm going to subtract this quantity from both sides, so minus that entire thing, 15 minus x in parentheses squared. So, I know h squared is equal to 49 minus x squared, and I also know h squared is equal to 144 minus 15 minus x squared. So I'm going to do a substitution. I'm going to take this and plug it in for h squared. Alright, so doing that, we get 49 minus x squared equals 144 minus 15 minus x in parentheses squared. So, alright, everyone's favorite, this is looking like a quadratic equation because we got these x squareds in them. So, to solve a quadratic, we know we gotta get it in standard form and set it equal to 0. So hopefully you know by now that this is not just that squared minus that squared, right? To do 15 minus x quantity squared, you need to do a little bit of work. Right, 15 minus x squared is of course 15 minus x times itself, right? That is what it means to square a number or a quantity. So that's going to be 15 times 15 is 225, minus 15x, minus another 15x, minus 30x, plus x squared. So all of that is in here. And let's distribute that negative now and clean this up. So 49 minus x squared equals 144 minus 225 plus 30x minus x squared. Alright, 49 minus x squared equals, combining those two, that's negative 81 plus 30x minus x squared. And you guys are in luck because these x squareds, if you add x squared to both sides, they cancel out. So, not a quadratic. I'm sure you guys are happy about that. But solving this, adding 81 to both sides, we get 130 equals 30x. And so x is equal to 13 thirds. Woo! Alright, so we did all of that. If you want, you can find the length of GJ and JI now by plugging in 13 thirds. But that's not necessary. What we were after is the height, right? Because that's the only thing we had to figure out. 1/2 base times height. So let's find the height using any of the formulas we have. I'm going to use this equation. Our height squared equals 49 minus 13 over 3 squared. So I plugged in 13 thirds for x. Alright, this is actually pretty difficult to solve. I know I've done it twice, but 13 thirds is 169 over 9. 49, I'm going to make that over 9 as well. So 49 times 9. Hold on, what is this again? 49 times 9. That is 441. H squared equals 441 minus 169. That's 272 over 9. Alright, we square root both sides. H is the square root of 272 over 9, which is equal to, so if you remember our square roots, square root of a fraction is the square root of the top divided by the square root of the bottom. So square root of 9 is 3. Let me just actually move this over here. Alright, square root of 272, that took me a while. But 4 divides into 272. 16 also divides in if you play around with it. And that's actually going to be 16 times 17 is 272. Alright, divided by square root of 9 is 3. So that is 4 rad 17 over 3 is our height. And so our area is going to be 1/2 the base, which was 15, times the height, which we just found as 4 rad 17 over 3. Alright, let's clean this up. 15 over 3, that's 5. I have a 4 on top, a 2 on bottom. That's going to be 2 on top. So 5 times 2 times radical 17. The area is 10 rad 17 square units. Alright. That was a nice problem. Alright. Some good practice there. So I'll stay over here for a sec in case you want to get anything down. Alright, so that was pretty difficult, I must say. But there is a much easier way if we use some trig. And we can do that if they gave us an angle. So I'm going to draw that triangle again. Again, not a right triangle here, even though it might look like one. Let's call this triangle ABC. And if that's ABC, then this is the length of A here, that's going to be B, that's going to be C. So I'm going to drop the height as before, and for this triangle the area is going to be 1/2. The base here is A, and the height is H. Alright, I'm going to do something a little weird here, and let's see what happens when I do it. So I'm going to take the area and I'm going to multiply it by B over B. Alright, so I'm multiplying it by 1. I am allowed to do this because, of course, that's equal to 1. So I'm not changing anything. And now I'm going to rearrange the way this looks just a tiny bit. So I'm going to swap the place of the H and the B. Right, that's H over 1. It's just commutative property of multiplication. So I'm going to change it to AB times H over B. So I changed the way it looks, but I didn't change the value of it. I changed the order. But these are still equivalent. Right, if you multiply out, the B's still cancel out. It's still just 1/2 AH. So the reason I did this is this H over B, that's pretty interesting. Let's take a look. H is here and B is there. What is that ratio H over B equal to? Well, since we're doing trig, you're probably thinking something about trig, hopefully. And H over B, well, if I'm looking at this angle here, angle C, that is opposite over hypotenuse. So I can say that sine of the measure of angle C is going to equal opposite H over hypotenuse B. So I can replace H over B with sine of C. And now we don't even need the height to get the area of a triangle. Wow, isn't that nice? It's just 1/2 A times B times sine of C. Alright, I don't want you to memorize these letters because this was unique to this triangle ABC, right? A random triangle could have any names for the vertices. So A, B, and C are just completely arbitrary. Right? A and B are just two legs, or any two legs of the triangle. And sine of C, well, this angle C, this was the angle formed by the two legs we used, right? The one with a length of A and the one with a length of B. So we call C the included angle. Can I do more? What did I do? Right. Anyway, two legs, and that's called the included angle. In other words, that's the angle between the two legs. Cool? So this is a way you can remember it, but A, B, and C really have no meanings, right? A and B, those are two legs, and angle C, that's the included angle between the two legs. Right? And just to show you that A, B, and C are arbitrary, I could have done the same thing by multiplying by C over C instead. So this could also have looked like 1/2 times AH times C over C. Right? Still multiplying by 1. Rearranging, A is 1/2 AC times H over C. So let's figure out what this ratio H over C is equal to. H over C, that is, if I'm using angle B, opposite over hypotenuse, that's going to be sine of B. So we also could have said A equals 1/2 A times C times sine of B. And again, what's important is if we look at these two legs, AC, right, A and C, angle B is the included angle there, the angle in between those two legs. Do not stop. No, cancel. Alright, hope I'm still recording. Alright. So, same thing. Two legs, angle between the two legs. Alright. So, just applying this, really basic problem, but we got two legs here, and the angle included between the two legs So we can say the area of this triangle is 12 times 9 times sine of 21 degrees. Alright, it says find the exact area and then round to the nearest tenth. So the exact area is going to be 12 times 9 is 108 times the sine of 21 degrees. And I'm just leaving it like that because sine of 21, that's irrational. It's not a nice ratio that we know either. It's not sine of 30 or sine of 45 or sine of 60, which we can rewrite. So we just leave it like that. But if you type that into your calculator, hold on, I know I have this somewhere. Scroll. That's going to equal about, oh, hold up. I forgot to multiply by half. Sorry. So that's going to be 54 times the sine of 21. And that is approximately, if you round, 19.4 square units. Right, I have the 1/2 up here, right? Okay, good. Alright, so exact area of this guy. We got 45 degrees, 75 degrees. And we have these two legs, but no included angle. So let's just find the included angle real quick. Alright, sum of angles in a triangle, sum to 180. Solving for that, that's 60 degrees. So the area here is 1/2. We've got the two legs, 12, and a length of 6 plus 6 rad 3, times sine of the angle in between the two legs, which is 60 degrees. And this is a bit of work, but 1/2 times 12 is 6. 6 times 6 plus 6 rad 3, sine of 60, we should notice as radical 3 over 2. Right, that's from our special right triangles. And distributing this 6 over here, we're going to get 36 plus 36 radical 3. Still need a parentheses because all of that's still being multiplied by radical 3 over 2. So now if I distribute this guy, well, I'm just going to rewrite it out first. 36 times rad 3 over 2 plus 36 radical 3 times radical 3 over 2. So simplifying, we're going to get 36 over 2 is 18. This becomes 18 radical 3 plus, again, 36 over 2 is 18. Radical 3 times radical 3 is radical 9, or 3. So that would be 18 times 3. And our exact area is 18 radical 3 plus 54 square units. Alright, typing this into a calculator and getting it to the nearest tenth, that is approximately 85.2. Alright. I like that one too. But here are the two best questions. Really number 3. Number 2 is the setup to get to number 3. But number 2, in the figure below, angle AEB is acute. You got this acute angle here. Show that the area of triangle ABC equals 1/2 AC times BE times sine of AEB. Alright, so we're going to be using this angle AEB somewhere. So I'm going to give this a name. I'm going to call this angle theta number of degrees. So we can refer to that as theta. And, alright, I'm going to do what we did at the start of today. And that is the area of any triangle is 1/2 base times height. So the base of this triangle is AC. Well, if I make that the base, it is the base, which means our height would have to be perpendicular to that base. So let's say that is BABC. We don't have a D, so let's call that D. So BD. And I'll label BD H, that's the height. So we said we're going to be using this angle. So what do we have? In this one we have the opposite height, and let's use the hypotenuse because that was in the original diagram. So I can say sine of theta is equal to h over be. Right, we want to get that height involved. So the area is going to equal 1/2 AC times, so let's solve for height in that equation. The height is equal to, multiply both sides by BE, you get BE times sine of theta. So plugging this in for that height, we get area equals 1/2 AC times the height, which was BE sine theta. And does that match this? Yes, it does. Theta is equal to the measure of angle AEB. So if I want, I can replace this with angle AEB, and they are equivalent. Alright, box that in. So this is going to let us do something extremely powerful, which is find the area of any quadrilateral. Alright, we know how to find the area of things like a kite, or a parallelogram, or a trapezoid, or a rhombus, or a square, or a rectangle. But any quadrilateral, that is some good stuff. This is wow. So we got this quadrilateral ABCD. We have W as the measure of the acute angle formed by the two diagonals, AC and BD. Showed that the area of ABCD is equal to 1/2 times the two diagonals, right? These are our two diagonals, AC and BD, times the measure of, times the sine of the measure of this angle, W. So there is a huge hint. This hint is so big, you can probably do this on your own now. But it says, apply the result from problem 10 to triangle ABC and triangle ACD. So we got two triangles, ABC, up there. And we got this triangle down here, ACD. So if I add the area of those two triangles, that's going to equal the area of the quadrilateral. Right, so we can say the area of a quadrilateral is going to equal the area of our two triangles. So the area of triangle ABC plus the area of triangle ACD. So let's figure out what the area of each of those triangles are. So if you look at triangle ABC, you'll realize, that looks exactly like this. Right, so we're going to just pretty much copy and paste this down here. So you can do exactly what we did above, and we can say that the area of this triangle is going to equal the base, or 1/2, the base, which is AC, times this guy. Alright, so let's give this a name. We can call this BE. Oh, and something I forgot to mention about this E. This E, by the way, could have been drawn anywhere, and this would still work, which I think is just pretty cool. So you will see that this is not dependent on where E is placed. So anyway, back to here. If we call this BE, well, that's going to be 1/2 AC times BE times sine of W degrees. All right? If you don't see where this is coming from, again, just follow the exact same steps we did over here, and you will get this. So that's the area of triangle ABC. Let me color code that in blue. Style blue. And let's find the area of triangle ACD now. So it looks like the same thing is happening. So this one's drawn a little differently. but if that's W degrees, then this is also W degrees by vertical angles. Right, that angle. Let me relabel this point E. So, how can we find the area of triangle ACD? So if you want, take a second to do that. But it's going to be the same exact way we just did earlier. I'll actually just redo it. The area of triangle ACD is going to be 1/2 base times height, as always. Our base in this case, if I make it AC, is going to be AC, right? And our height, well, the height to AC is going to be this guy, right? It's going to be outside the triangle, which is fine. But that's going to be our height. So what is that height equal to? Well, if I use W degrees again, right, and I take the sine of that angle, sine of W is going to equal opposite. And looking at this triangle, right, the opposite is H over the hypotenuse of that triangle is ED. So the height for this guy is ED times, again, sine of that same angle. So AC times ED times sine of W. Alright, so I'm going to take this piece here, copy that, and that was the area of triangle ACD. Plus. Alright, so the area of our quadrilateral ABCD is equal to this huge mess. But if we look, we got a lot of like terms or common factors. They have a half in common. We got an AC in common. We got a sine of W in common. So let's pull out all of those common factors. 1/2 times AC times sine of W times what is left over. We have just BE and ED left over. So times BE plus ED. Well, let's look at this diagram. What is BE plus ED? BE is that, ED is that. Oh my goodness, that is just the length of the other diagonal. They combine to form BD. So this is BD from the diagram. So it's 1/2 AC times sine W times BD. And reorganizing it, we have 1/2 AC times BD times sine of W. And that's the area of that quadrilateral ABCD. And in fact, this will work because we did this all with letters, and in general, this is going to work for any quadrilateral, right? So again, don't memorize these letters, right? They don't mean anything. The formula is area of any quadrilateral is 1/2 times the length of the two diagonals. So I call it diagonal 1 and diagonal 2 times the sine of the acute angle formed by the two diagonals. Sine of the acute angle formed by the diagonals. And that is a fantastic result that we can now use. Alright, so the area again of a quadrilateral is 1/2 times the area of a quadrilateral is 1/2 times the product of the two diagonals times the sine of the acute angles formed by the diagonals. This is the area of any quadrilateral. right? And that includes kites, that includes rhombuses, and rectangles, squares, parallelograms, right? In fact, for a kite, I don't know if anyone remembers this, but the area of a kite is, or was equal to, or still is, 1/2 times the two diagonals, right? So if we try to apply it to this formula, well, we don't have any acute angles in a kite because they're all right angles, but that doesn't matter. If we pretended that was our acute angle, well, what is the sine of 90 degrees? If we just add that on, sine of 90 degrees, well, that's equal to 1. So this formula still, of course, holds even for a kite, right? A kite's really just like a special case for the area of a quadrilateral. So anyway, hope you enjoyed that. I like this. This was really nice. So yeah, any questions, again, send me a message on Classroom. Today's lesson was fairly simple, I think. All right, we got this formula that you got to know how to use and apply, and also this one. All right, so have a good weekend. All right, remember our test is on Monday, and I'll see you guys soon.